Now, when I'm faced with a pretty complicated equation like this, you can imagine I'm going to be writing down the terms in this equation over and over again. It's going to get pretty messy. It's not a simple equation to solve. One thing that we know how to do, though, that will make our jobs a lot easier is if we can get rid of, once again, all of the fundamental constants. So I want to switch now to natural units. That's always one of our first approaches to solving this type of an equation. If I go now to natural units, in natural units, what I'm hoping to do is to ensure that this combination h bar squared over m, that comes into my kinetic energy, and notice, by the way, very nicely, it's the same exact combination h bar squared on m that enters in the fundamental constants in the centrifugal potential, so I can kill two birds with one stone. If I insist that h bar squared on m should have a numerical value of 1. The dimensions on it we see, well, if I take that constant and I divide by r squared, I get energy. So the units on this constant must be energy times distance squared. So that's 1 unit energy times unit length squared. The other set of units we have to deal with, the other set of constants, just comes in here in my Coulomb part. So that will be z Coulomb's constant e squared. I also would like that to have a numerical value of 1. That combination divided by distance gives me an energy. So its dimensions are energy times unit length. So that will be 1 unit energy times a unit length. And this then is equation 1. This is equation 2. And we've done this kind of thing before. We know how to solve to get our natural units. When we do that, we'll have equation 1. Notice if you divide it by equation 2, if I look on the right-hand side, the energies cancel out perfectly. I'm just left with 1 unit length, and that is really a beautiful result. Now that result, 1 over 2, then tells me that the unit length is going to equal h bar squared will be on top. There will be an m on the bottom. And when I divide by 2, I'll get a 1 over z, which I'm going to factor out. And that then multiplies the Coulomb's constant times e squared. Coulomb's constant e squared. So you see there's really two portions to my natural length unit. The first portion is this 1 over z part. And this is kind of sensible. The unit length basically tells us how big our atom is. It tells us the units in which we should view these solutions that we're going to find. And what we're finding is that when we translate them back into traditional units, our unit length actually is shrinking as I increase the strength of the nucleus. And this actually makes a lot of sense, right? If I make a more powerful nucleus with a stronger attraction to the electrons, it's just pulling the electrons in towards the center. So this term just says that the atoms shrink, right? They get smaller with increasing z. The second piece then is a set of constants we've actually seen before. There's a name for this. This is called A naught. The unit it's often referred to as is the Bohr unit, so it's also defined as 1 Bohr. And in traditional units, this works out to be 0.529 angstroms. And that's something we've seen before. That constant actually showed up in our solution using the semi-formal methods, the Bohr-Sommerfeld solution for the hydrogen atom. This was known, again, as the Bohr radius. So this gives me the size of my hydrogen atom. And when the hydrogen atom has a which has z equals 1, actually would have this as its basic unit length. So this is looking quite promising from facts we know experimentally in nature and compared to our previous semi-quantitative analyses. Very good. We also, though, need to know the energy unit, and this will teach us its own other lessons. So for the energy unit, I want you to notice that I can get it by combining these equations. If you look at them a little while, you'll see this. If I take equation 2 squared and divide it by equation 1, on the right-hand side, I will get energy squared times length squared, divided by 1 energy times length squared. That will just leave me with 1 energy. And when I square equation 2 here, on the other side of the equation, I will get something that goes like then z squared, which I again will factor out. I then have to square the Coulomb part times e squared, so that will become squared. I then divide by 1, which means I'll be dividing by h bar squared. And finally, the m flips over from the denominator into the numerator and multiplies by the numerator. So there'll be an m also in the numerator. This again has these two different components. This z squared tells me how the energy increases as I strengthen my atom. And this squared also makes sense because there are two things going on at the same time. First, as I increase the strength of my nucleus, I'm sucking my electrons, pulling them in closer by a factor of z. And secondly, the Coulomb, the charge on the nucleus, is z times stronger. So it makes sense then the total effect will go like z squared. So energy, so that's the conclusions that we learned from that one, is that the energies then go up in proportion to z times z equals z squared. And it's a factor of z because you're closer, and another factor of z because you are stronger. Finally, we can also look at this key quantity, which is our key unit of energy. This also has a traditional name. It's called the Hartree. So this is 1 Hartree. And in traditional units, this has the dimensions. This works out to be approximately 27.21 electron volts. Now, that number should look very familiar to us. It's actually exactly twice the ground state energy of the hydrogen atom, which is 13.65 electron volts. So we've really seen all of these types of quantities before. So it's very consoling that they are going to be our natural units of length and energy. To just complete the connection, I would like you to remind you about what we actually know. So in particular about the hydrogen atom. So reminder regarding the hydrogen atom. And that is that we've solved it before with the Bohr-Sommerfeld techniques. And the Bohr-Sommerfeld solution for this, and remember the hydrogen atom of course has Z equals 1. So the Bohr-Sommerfeld solution that we found, which actually matches the experiments exactly. And that's what's so beautiful about this, right? Because now we know exactly what we want to compare to, because this actually will match the experiments. If we can reproduce this formally, we've done it. And we've gone all the way to the beginning of the course, and we've now actually done formally the solution for the behavior of this atom that we began everything with. Now, that energy in the Bohr-Sommerfeld solution for hydrogen comes out to be minus 13.65 eV divided by n squared, where n is an integer that actually this n starts from 1 and counts upward, like so. And if we want to rewrite this in natural units to see what kind of solution we're looking for, you will notice that the minus 13.65 is actually exactly minus 1/2 of an energy unit. So this would be minus 1/2. And then the remainder is just the same formula, 1 over n squared. So this is what we are hoping to check against. This is the actually also the experimentally observed result. It's experimental result. And I will put a box around that. That's the experimental result in natural units, because this then is the formula that we're hoping we're going to be able to prove.